Okay, so you're welcome to my channel, and in this video, we're going to talk about linearity and homogeneity of partial differential equations. Okay, so let me add this one of partial differential equations. So we're first going to talk about what linearity means. What do we mean by a linear operator? Okay, so a linear operator, or an operator L, is said to be linear if when it is operated on a constant times u, where we see u to be, the solution, then what we're going to have is, or the dependent variable, let me put it that way, yeah, we're going to have it being equal to the constant multiplied by the operator acting on the dependent variable. At the same time, if we have two dependent variables, then what you're going to say is that the operator acting on these two should be the same as the operator acting on one plus the operator one acting on the other. Okay, so we can sort of, squeeze these two conditions together and say that L is linear for solutions, or let me call, okay, for solutions, because we are talking of partial differential equations here, so it's okay. So it is linear if, when I have the operator acting on a linear combination of these solutions to be equal to a L of u plus b L of v. Now you can see something very, very profound here, okay, or something very, very interesting here. We are going to talk about it later in the video. Okay, so one thing I want to do is that if I'm given a PDE, I want to be able to tell whether this PDE is linear or not. Okay, so given a PDE, so for instance, let's go for the simplest PDE. So you have maybe ux equals 0. Okay, what you want to do here is, let me write it well. What you want to do here is to write the PDE. So you want to write the PDE as the operator on u being equal to whatever is going to be on the right hand side. It could be a g, but mostly 0. We want to write it as this. And what we want to do is that, is this going to, that is going to give us, we are going to know the operator from this. Okay, we're going to know the operator from this, and once we know the operator, okay, what we can do is to check whether the PDE is linear or not, because if it is linear, then it has to satisfy the condition given above. Okay, yes. So let's, oops, okay, so if, oh shoot, so if the PDE is linear, then we expect that L of the AU, so call it AU1, then B of U2 should be equal to A of LU1 plus B of LU2. So that's what we want to know, okay? Yes. So how does this transcribe, or how does this come into play in a real example? So for instance, let's say I'm given example, I have ux plus uy is equal to 0, and this is going to be a transport equation with a speed of 1. You're going to see all these things, but here what we are trying to do is to write this as an LU equals 0, right? So we know that this is the same as del x of u plus del y of u. We've talked about this in our previous video, so you should know that. And now you can have u all out, and this is going to be del x plus del y is equal to 0, right? Okay, so what is your L over here? Your L is del x plus del y. Okay, so that's your operator. So if this is going to be linear, then we know that for u and v solutions of the PDE. Okay, we want to do L of AU plus BV, and that is going to be del X. Oh, all right, so this is going to be del X plus del Y, and that is multiplying AU plus BV, and this is actually going to be, if you try to expand, open the brackets, expand, you're gonna have del X of AU plus BV plus del Y AU plus BV. Okay, and that is going to be equal to A del X of U plus B del X of V plus A del Y of U plus B del Y of V. Oh, my bad. Of V. And that is going to be, look at these two and look at these two. I can have A del U del X plus del U del Y, then plus B del V del X plus del V del Y. Okay, now comparing this to the original PDE, which is given in the question, what is del U? What's going to be del U del X plus del U del Y? What is that going to be? Yeah, from the original one, what do you think is going to be? This over here is going to be the L of U, right? And this is going to be B, the L of V. If you want to know why, you can just send the U out and then you should see that clearly. So this implies that the PDE is linear. Okay, yes. And then one thing you get to know is that you can use this method to show whether a PDE is linear or not. But another easier way, or an easy way, is that for linearity, anytime you have a PDE in which you don't see transcendental functions of the dependent variable, I mean, if you don't see tan u, you don't see exponent of u, you don't see log of u, all those, if you don't see any of these in the PDE, at the same time, if you don't see powers of u and products of u and its derivatives, then you always have a linear PDE. Okay, so for example, when I pick this over here, you don't see any product of u and its derivatives. You don't see u having a power of 2. You don't see transcendental functions of u and all those stuff. So it makes this a linear function. But I want you to try by yourself. Show me that u squared plus uy is not linear. It's not linear, okay? By the same thing we did it over here, you can try that here, and that should tell you that it's not linear. And this is non-linear, okay? It is non-linear, okay? And also I want you to tell me that tan of u plus maybe u x is equal to 0 is also not linear, using the same idea. Okay, yes. So that is one thing about linearity. And then one thing I want you to know about linearity is that the the positive or the benefits of linearity is that if I have or given two solutions, okay, given two solutions U and V of a PDE, okay, a PDE, what you can say is that if the PDE, sorry, by linearity, okay, by linearity, AU plus BV is also a solution, okay, which means that if I have solutions U1, U2, all up to UN, by linearity, the summation I starting from 1 to whatever n it is of the CI's, where the C's are some constants, of these UI's is also a solution. That is one positive thing about linearity. So if these are solutions, then the summation of that is also a solution. That is why you always have the law of superposition in differential equations. You are always told that, oh, by the law of superposition, if this is a solution and that is a solution, then a linear combination of the two is also a solution. It all comes down, or it all comes from the linearity property of the PDE, or of the operator, sorry. Okay, yes. So I'm not going to do homogeneity in this video. I'm going to do, let me just add it. So if you're given any PDE, so a PDE where you have, f of x, y, z, and the derivatives, okay, derivatives x, maybe u, y, t, all this stuff equals 0, okay, then that is, oh no, okay, so now let's just talk of the homogeneity pretty quick and let's just move on. So if I'm given L of u, that's a differential any partial differential equation that can be written as this: Lu equals 0, then that is a homogeneous PDE, okay. However, if L of u is equal to some g, all right, maybe of x, u, x, y, up to t, it doesn't matter, however it looks like, then what happens is that we have an inhomogeneous PDE, okay. Yeah, so for example, the typical example we use, ux plus uy equals 0. This is homogeneous, but u of x plus uy equals tan of maybe x, y. This is inhomogeneous. Okay, yes. So this is going to be the end of the video. If you like the content of the video, leave a thumbs up and subscribe to the channel. There are more to come. So in the next video, I'll probably talk about what do I even talk about? Yeah, so we're going to talk about, first order linear. Alright, so in the next video, we're going to talk about first order linear equations specifically and try to solve them. We're going to see how to solve differential partial differential equations. Okay, now we know a lot about these partial differential equations. Now we want to know how to solve them, and we're going to do those in the next video. See ya.